Alright, so let's see where we left off in class. So let's just rehash really quickly. The Euler's method is going to be a way for us to find a numerical approximation of a differential equation at a specific value. And it's not on this page, but this page, here we go, where we came up, or not came up with, but we wrote the equation that's going to allow us to do the numerical approximation. And it's basically just a process. You keep repeating the equation until you get to the value that we're interested in. And this is the one that we got through in class. And we kind of started the idea of doing the same equation, which you guys had to change some of this, and I think you're going to have to do some more of that as we go through it, so make sure you make the changes as we go. Um, this equation right here is the same equation as the previous problem, but this time it's going to be more steps because now we're counting by 0.1s for delta x as opposed to 0.2. So um, let's go ahead and I'm going to write out the first couple of these just to make sure you guys are doing this all right. The biggest thing again is plugging these things into your calculator correctly and writing down all of the decimal points. It's a little bit tedious, but it is important because otherwise at the end your answer will be off. So let's see, the previous y value is 4 plus delta x, which is 0.1, times the derivative evaluated at the previous x and y. Once again, this is only dependent upon y, so I'm going to plug in 4 for this and get 2. So it looks like we're going to get 0.1 times 2 is 0.2 plus 4, 4.2. Okay, not usually too hard on that first step, especially when you're given whole values up here. Okay, next step. Bring down the previous y that we just found, plus, it'll always be the same delta x. Now I have to plug in the previous x and y, which would have been 0.1 and 4.2. Plugging in 4.2 into this y value here is going to give us 2.2. And that's going to be 0.22 when you multiply it by 0.1. And 4.2 plus 0.22 is 4.42. Yeah, that's right. Okay, bring down the y, 4.42 times 0.1. Evaluating this at 4.42 gives us 2.42. And that's 0.242 added to this is going to be 4.662. Okay, bring down this. Previous y, 4.662 plus 0.1. Plugging that in, subtracting 2 from that gives you 2.662. This is going to be 0.2662 added to this. It's actually going to be something you have to do some carrying. You could get 4. What is that? 9282. Yeah, I won't be doing this next one probably without a calculator. So 4.9282 plus 0.1. Subtracting 2 from that is going to give you 2.282. And when you plug that into a calculator, you're going to get 5.22102. And again, you need to write all these decimals out. And with the next ones, it gets even longer. So 5.22102 plus 0.1 times, subtracting 2 from that, you get 3.22102. Plug all that in your calculator. And this is the one where you can truncate because it's the last one. You end up with 5.543. I think that this could have been rounded up. I don't remember the last decimal place on there. That means that with our approximation with a delta x of 0.1, y of 0.6 is approximately 5.543, as compared to If we did this with a step size of 0.2, the previous one, the estimate was 5.456. So just slightly bigger with the next approximation, 5.546, 5.543. Yeah, just a little bit bigger. We're talking about, I don't know, what is that, about 0.09 or so difference. Not bad. That means the approximation here is probably pretty good. Obviously, if we wanted to make it a better approximation, instead of counting by 0.1, we could count by 0.05 or 0.01, which would be an enormous amount of steps here, but we could do that. We're not going to, but we could. All right, so what's different about this one is that this time the derivative is now dependent upon both x and y. The derivative is 2xy. We're going to start at x is 1, y is 3. That's our initial condition. We're going to have a step size of 0.2, and we're going to try and approximate y of 2. So again, let's create a chart. This is your x sub n. And again, if you get good enough, you can just kind of write your y sub n out here. You don't have to write what it equals, but for this one, I'll go ahead and write it again. It's y sub n minus 1, or the previous y, plus delta x times the derivative evaluated at the previous x and the previous y. And that equals your current y. So let's start with the current x, which is 1. The current y is 3. And we want to go up to 2, counting by 0.2. So 1.2, 1.4, 1.6, 1.8, and 2. And this is where we want to end right here. So I am not going to go through the entire process. I'll do the first line, and then after that I'm just going to write down what the answers would be. Please make sure you're checking these with your calculator to make sure that you can actually get these. Because you will see problems like this again, and you're going to have to be able to use your calculator to do it. So the first one, you bring down the previous y, which is 3, plus the step size 0.2, times the derivative evaluated at the previous x and y. Now this time I do have to plug in x is 1, y is 3 up in here, and when I do, I get 2 times 1 times 3, which is 6. Maybe I'll do one more. So that's going to be 0.2 times 6 is 1.2, plus 3 is 4.2. Excuse me. All right, so 4.2 gets plugged in here, plus the step size, times, now in this case, it's going to be 2 times the previous x and y, 2 times 1.2 times 4.2. That's the previous x and y. And when you plug, oops, one more parentheses, when you plug all that stuff in, you end up with 6.216. Bring that one down, start the process over again. So these are the values that we should end up with. You should end up with 9.69696. The next one's starting to get pretty long, 15.9030144. And again, write them all down. You need it. And then for the last step, this is the one you can actually chop off or truncate at 3 decimal places. I get 27.353. All right. So that means that y of 2, according to this, with a step size of 0.2, is approximately 27.353. What I can tell you, because I know what's coming, is that this is not a very good approximation for this one, for whatever this original equation was that came from. And we could find this original equation, and we will eventually, just not now. Again, the main reason we do this is because a lot of these you cannot. All right, so how could we make this a better approximation? Well, we could let the step size, instead of being 0.2, we could count by 0.1. That's the next page. This one I am leaving pretty much up to you guys. I will tell you what the answer to this one is supposed to be. It is your job to be able to try and match this. Please make sure that you attempt to do this to give yourself some practice. You'll see problems like this, again, on your homework, web assign, stuff like that. So I can tell you that with a step size of 0.1, it's the same derivative, same starting point, same thing that we're trying to approximate. Y of 2 is approximately, after you do the 10 steps, 37.905. So we could talk about that just for a second here. The fact that this is only 27.353, this one is 37.905, and I can tell you that this is actually not a very good approximation, which means the first one was really bad, and it jumped by 10. So that's a pretty big difference there. That's making the step size 0.1. In order to make this a really strong approximation, this step size is going to have to be much, much smaller. We're going to have to take a whole bunch of steps to make it a really good approximation. And it would actually be kind of interesting to figure out what would you have to make the step size to make the actual thing pretty accurate. Well, in order to do that, you'd obviously have to know what the original value actually is of y of 2, which means we'd have to know what this is. So that's what's coming here. This is one that you're going to have to make a correction on your paper. Your paper right here says 3x to the x squared minus 1. It should say 3e to the x squared minus 1. So change that. This right here on your paper is wrong. Change that to e, because yours says x. Without going through how to do this yet, because we will do that eventually, I can tell you that the exact solution, so if I took the antiderivative here and solved this thing for y, the exact solution to this is this. That's what you come up with. Y equals 3 e to the x squared minus 1. This is the original equation that this derivative came from. Which means if I actually want to find out what y of 2 is, simply plug in 2 for x. 3 e to the 2 squared is 4 minus 1. So 3e cubed is the exact answer. Well, that doesn't tell us anything as far as the decimal is concerned. So let's get the decimal approximation for that. And that works out to be 60.256. That's a pretty big difference between the 27 and the 37 point somethings that we got from the previous problems. So going down to the next question, you should be able to tell this pretty easily. Which value of x equals 2 gives a better approximation? Examples 3 or 4. Obviously, 4 gives the better example. It's closer. Example 4 gives a closer approximation, and a more mathematical way of saying that is that the error, or the difference between the actual value and the estimated value, is less in 4. And we need to talk about this thing called error, because it will ask you that on some of the problems. And the error is simply going to be the actual minus the estimated. And that's the error in one of these things. So we could find the error for 4. The error for number 4 would be 60.256 minus, let's get the actual value that we had, it was 37.905. 37.905, and I did not have this one worked out, so I'm going to have to work that out real quick. 60.256 minus 37.905 gives you an error of about 22.351. That's actually a pretty big error. You could certainly calculate relative error and percent error by doing a division, but not worried about doing that right now. So the error is pretty big. In either case, the number 4 is going to give you the closer one because it's less distance, it's less error. And then the obvious answer to this, how could we obtain a better approximation by using Euler's method, should be to simply use a smaller delta x. use smaller delta x, some kind of change of x. And again, the idea would be the smaller and smaller that we make delta x, the more precise the values are going to be. All right, that finishes us off. You should have enough to finish up.